Hi everyone, so in this video I'm just going to go through the questions I set from the Chemistry Cubed book one by one and give an explanation of why each of the answers is what it is. So the first one was question 2, and that gave you a list of metals and asked which of the metals would react with a dilute acid to form hydrogen. Now, if you didn't find it very helpful, they said to look at a table on page 1145 to help. That table is actually the standard reduction table. Table 25.1, and it's actually on page 1142. But I've copied it here and also given the value for barium because that isn't in the book. And down here I've copied a paragraph from the first video which said that most metals with a negative standard reduction potential will react with an acid to generate hydrogen. So that means that in this question, tin, that has a negative standard reduction potential, so that will react. Silver, that had a positive one, so that won't. Barium, I had to get this one off the internet, it's quite negative, that certainly will. Nickel also has a negative standard reduction potential, so that will. And mercury, that has a positive one, so that won't. It's good to know that there are some exceptions to this rule, and they're mentioned in the book. That in some cases reaction that would happen, such as aluminium is a good example. Aluminium has a standard reduction potential of minus 1.66. However, this won't react with a dilute acid to generate hydrogen, and this is because the aluminium will always form like a surface oxide layer, and this oxide protects it. Question 3 gave us 5 compounds and asked us to assign the oxidation state for each of the elements in all of the compounds. So let's start by doing the hydrogen in each of them, because this is the easiest way to start. Now we know hydrogen can either be +1 or -1 oxidation state. That's it. And that just depends on whether the thing it's bonded to is more or less electronegative than hydrogen itself. So you see hydrogen itself is here with an electronegativity of 2.2. So lithium is only 0.98. Therefore, where hydrogen's more electronegative, it's going to be in the -1 oxidation state. With the second example, iodine is more electronegative than hydrogen, so hydrogen is going to be in the +1 oxidation state. With ammonia, again, nitrogen's higher, so ammonia, the hydrogen's in the +1. With the silicon, it's hydrogen in the -1, and with borane B2H6 we can see that boron is also less electronegative, therefore hydrogen's in the -1. Now with oxidation states, in a neutral compound such as all of these, the oxidation state has to add up to 0. So if we go through and then follow that rule to complete them, we see that lithium needs to be +1, iodine needs to be -1, nitrogen, because there are 3 hydrogens that are each +1, this then needs to be -3, because in the case of the silicon hydride, because there's 4 -1 hydrogens, this needs to be +4. And in this case, which I guess is the trickiest question, that's why it's last, there are 6 hydrogens in the -1 oxidation state, so it's at -6, but because there are 2 borons, each of these just needs to be +3. So question 4 is asking us to look at the reactions of some hydrides from throughout the periodic table and asking us to predict the products and write balanced equations for these. So the first one's quite simple. We're looking at cesium hydride and the reaction with water. And if you remember, we said that all the group 1 metals and also all the group 2 metals with the exception of beryllium will react with water to produce an alkaline solution and hydrogen. So in this case, cesium hydride reacts with water to form cesium hydroxide, which is alkaline, and hydrogen. The other thing we know about this reaction is we talked about the stability decreasing down a group, and cesium's right at the bottom of group 1, so this will be quite a violent reaction. It will happen with ease. Next, we're looking at the reaction of borane with pyridine, which is something I talked about in the discussion session as well. It can also be thought of as the reaction of borane with a Lewis base, so something that can donate an electron pair. If you're not familiar with pyridine, it's an organic ring-shaped compound with a nitrogen in the ring. So it's very similar to benzene, but with a nitrogen replacing one of the carbons. And what happens when you react borane with a Lewis base is it will break the borane down into two BH3 groups, which are electron deficient. So if we show them here, BH3. Now this boron only has 6 valence electrons, so it hasn't satisfied the octet rule. There's a gap here where another electron pair could go. And that's exactly what will happen. The lone pair on this nitrogen, which in the case of pyridine, it could also be ammonia or THF as an example in the book. That's another organic ring-like structure like this, but with oxygen in there, that will also have a lone pair. This can then coordinate there, satisfying the octet rule. And there's a couple of ways you can write this equation and also indicate the special nature of this bond, because this isn't a covalent bond. It's not a sharing of equally of electrons between the boron and the nitrogen. It's called an adduct. Both the electrons are coming from the Lewis base from the nitrogen and associating to the boron. So as I said, there's 2 ways we can write that. The first one is with the chemical formulas. We can say B2H6 plus pyridine, which is NC5H5, goes on to form, as we said, the BH3 groups with the pyridine, NC5. And then we can put the charges on top of, we show the bond, and we can put the charges on top to show that the boron's negative because it's taken up some electrons from the association, and the nitrogen's slightly more positive than it was because it's kind of donating its electron pair somewhat. And to balance it, remember, we've broken the B2H6 into 2 BH3s, so we're going to get 2 adducts, and it's reacting with 2 equivalents of pyridine. The other way we can show it, because sometimes, it's not obvious, especially if you're not familiar with the organic compounds, that this is pyridine. We can also just say B2H6 plus PYR, which is a common abbreviation for pyridine, or 2 pyridines as we've already seen, goes on to make 2 of these adducts. And another way you can show adducts is just with BH3 and then a dot in the middle and pyridine there. Now the third example is a reaction of silane with oxygen. And now there's a lot of oxygen in the air, so we can think of it as the reaction of a silane in air. And the reason these react with air is because they're slightly further down the periodic table. If you look at carbon above it, so that we also have the carbon equivalent, which would be C2H6, which is ethane, that doesn't react spontaneously with air. But because we're going down the group, they're less stable. Si2H6, this silane, will react spontaneously with air to form an oxide and water. So we've got Si2H6 and oxygen going to form silica and water. And this one's quite tricky to balance. There are numbers everywhere. So it turns out that 2 equivalents react with 7 of oxygen in the air to create 4 equivalents of silica and 6 waters. And you can check this. We've got 4 silicon atoms here, 4 there, 12 hydrogens. We've got 12 hydrogens here, and then 14 oxygens, and they're made of these 6 oxygens here, plus the 8 oxygens in the silica. The final question is looking at the reaction of hydrazine with nitric acid in water, or an aqueous solution of nitric acid. And this is important and almost a trick question. because therefore we're actually looking at the reaction of a strong acid in aqueous solution with hydrazine. So how we can actually show it is this N2H4 plus H3O plus. Now this is because this is the hydronium ion, and this is what's formed when water is protonated by a strong acid in solution. And all that happens here is that the hydrazine gets protonated to make the hydrazonium cation. So we end up with N2H5 plus in water. Question 5 is a very interesting one because it's asking us to look at why one compound will exist while another seemingly very similar compound won't exist. And this has to do with a number of things such as oxidation state and the thermodynamic stability of products versus theoretical products. So let's start by looking at the oxidation state of it, because that gives us a really good indication off the bat of which will exist and which won't. So first off, I'll just write at the top here the electronegativities of the three things we're looking at. So hydrogen has an electronegativity of 2.2, sulfur has an electronegativity of 2.58, and fluorine has an electronegativity of 3.98. So in the case of SF6, the fluorine is going to be in the minus oxidation state because that's going to have is more electronegative, so that's going to be in -1, and the sulfur is going to be in +6 because it's, as we said in one of the earlier questions, a neutral compound has an oxidation state of 0, so it needs to all balance out. If we go the other way, in this case, sulfur is the more electronegative, so hydrogen will have a +1 oxidation state, and there's 6 of them, so it's very hard to write at the top of the screen. There's 6 of them, so the sulfur will end up having a -6 oxidation state. And you'll get a feeling for what a common oxidation state is as we go through the lectures. But in this group, sulfur having a -6 oxidation state is very unstable. It doesn't happen. So that gives us the first indication that this probably won't happen. Now the way of looking at it is what are the alternatives? So what can happen is we've got SH6, and we know from the lectures that if we were to get a hydride of sulfur, it's most likely to be H2S, and therefore it will make a couple of hydrogens as well. Now this delta H of reaction will be a very, very large negative number. That is because the HH bond, if you remember, is a really strong bond. It's over 400 kilojoules per mole. And that means that this reaction releases a lot of energy because it's making some really stable compounds. If we look at SF6, on the other hand, if we say that makes F2S plus 2F2. Now the fluorine-fluorine bond is nowhere near as strong as the hydrogen-hydrogen bond. So the delta H of reaction, even if it was negative, would be very small. And therefore it won't be so favourable to make these products. It's actually more favourable for it to just stay as its own, as the compound. So yeah, there you go. It's kind of a mix between the oxidation states give you a good indication of why it's unstable, and then going from that we can look at how thermodynamically stable the alternatives are, and if there is a very big stability gain, then it's likely to not exist. Question 6 is going back to something a bit simpler, classifying hydrides as whether they're ionic, covalent or metallic, which I found was a bit unfair because they don't really talk about it in the book. And for the covalent ones, do they have a bridging hydrogen? So I've taken the periodic table that we had in the lecture videos that actually shows us which are ionic, which are electron deficient covalent, which are electron precise covalent, and which are electron rich covalent. So, and the general trend was with the S block, with the exception of beryllium, they're ionic. But as I was saying, with the exception of beryllium. So the beryllium hydride is actually covalent. pH3 we can see is on the right hand side here, and the P block ones are all covalent hydrides, so this is also covalent. Potassium hydride is on the left hand side in group 1, therefore that one's ionic. HCl is from the P block again, so that one's covalent. And the one I found quite mean, iron titanium hydride, which doesn't even have a stoichiometric formula. This is a metallic one. I felt this was unfair because, in the book, it does actually say on page 1154 about metallic hydrides, but it is half a sentence. And essentially, if it makes if hydrogen bonds with transition metal, so group D that we haven't looked at in the middle here, it will make a metallic hydride. The next thing, it was asking us with covalent hydrides, do they have a bridging hydrogen? Now these are the ones that have the 3-centered 2-electron bonds, like the boranes. So it's these electron deficient covalent hydrides that I've just highlighted. So beryllium hydride is electron deficient, and that has a bridging hydrogen. The pH3 is electron rich, so that doesn't. And the HCl is also electron rich, so that doesn't have bridging hydrogen either. Question 7 is quite a short question, and it doesn't even have an answer at the back of the Chemistry Cube textbook. We'll go through it quite quickly. Why isn't plumane well characterised? And the short answer is it's very unstable. It doesn't last for very long at all. So if you remember, the stability of hydrides decreased down the group. Now lead is at the very bottom, or nearly the very bottom, of group 14, under carbon and silicon. And because of this, it's so unstable that even if it does form, it's going to be very thermodynamically unstable. It's going to want to decompose and form hydrogen and lead. So therefore, even if you can make it, it's very short-lived. And this means that we can't really study it or find out anything about it, which is what the word characterised means. The question 9 is another thermodynamics question, and it's actually using the Born-Haber cycle like we did for the lattice enthalpies in the last lecture. And it's really important to be able to do this because we can use them a lot to work out what's stable, how much energy is required for a reaction to occur, and things like this. So we've been given these 3 bond dissociation enthalpies, the hydrogen bond dissociation, the fluorine bond dissociation, and the HF one. And we're asked to calculate the enthalpy change of HF. So we're going to have to create our own enthalpy diagram first. So we start by the reaction of hydrogen plus molecular fluorine to make a molecule of HF. You remember from the lecture, this is the only hydride that can actually be made by simply combining the gases. Now, the tricky bit of this question is getting the balancing right and seeing how that affects your calculations. So we'll see this isn't balanced yet. We actually make 2 moles of HF when combining molecular hydrogen and molecular fluorine. And we want to calculate the delta H of formation, which is this energy. So let's look at the individual steps of the reaction. So first off, the molecular hydrogen is going to break up into 2 hydrogen atoms, and this is 436 kilojoules per mole. The same is going to happen with molecular fluorine to make 2 fluorine atoms, and this is with a bond dissociation of 159 kilojoules per mole. And then these 2 will combine to make 2 molecules of HF. Now we're given the bond dissociation energy of HF as 570. And this is how strong the bond is to break the dissociation energy. If we want to make this bond, it's just the negative of it. So then this is minus 570 kilojoules per mole. So essentially we can follow this diagram round, following the arrows and adding up all the enthalpies to get to HF. What we need to take into account though is that with these values, the dissociation, it's going from a molecule to 2 hydrogens and 2 fluorines. And with this dissociation energy here, we're actually only making 1 mole of HF. So there's a couple of ways we can go about it. I'll take you through both of them. The first one is that we only want to have 1 hydrogen reacting with 1 fluorine to make HF, and therefore we can use half of these values. So then if we take the delta H information as being half of the bond dissociation energy of hydrogen, and therefore 218, adding that with half the bond dissociation of fluorine, which is say 80 to make it simple, and we're doing positive signs because we're following the arrows, and then we take away the bond dissociation energy of hydrogen fluoride, and we're doing the whole value of this number because you can see here it's for HF, and this gives you 272 kilojoules per mole, or minus 272 kilojoules per mole, sorry. Now the other way we can do it is by working out the formation of the 2 hydrogen fluorides. So in this case we can take the whole value of the bond association for hydrogen, 436, adding it with the whole bond association for fluorine, 159, and taking away 2 times the bond association of hydrogen fluoride. Now remember, we're doing it 2 times because we're making 2 moles of HF. So minus 1140. And if we plug this into the calculator, it gives us minus 545 kilojoules per mole. Now remember, this is for forming 2 molecules of HF, and we were actually just asked for the formation of HF. So if you divide this by 2, we end up getting, again, minus 272.5 in this because of the rounding. So that's how you can use a Born-Haber cycle to work out the enthalpy change of formation. In question 10, we're taking a look at hydrogen bonding and how we can look at the trends in the strength of hydrogen bonding in different molecules. And hydrogen bonding, if you remember, is all to do with electronegativity, as if we've got hydrogen bonded to a more electronegative element, and we'll take this HF at the top as an example, the fluorine, because it really likes electrons, will end up with a partial negative charge on it, and the hydrogen will end up with a partial positive charge. And these partial charges will have attractive forces between them, especially in examples like HF, where fluorine has such a high electronegativity. They're really getting quite big partial charges, so the bonding can be quite strong. So I'll write up here the electronegativities of the 4 elements of interest. So fluorine is 3.98, oxygen is 3.44, hydrogen is 2.2, and sulfur is 2.58. So you'll notice in all these cases, hydrogen is the more electropositive element, so it's always going to have a partial positive charge, and the other one is going to have a partial negative charge. The only difference is how big the difference in electronegativity is. And the bigger the difference, the bigger the partial charges, and the bigger the strength of the interaction. Therefore, the trend will be going down here. Hydrogen bonding weakens. So HF has the strongest hydrogen bonds and SH has the weakest hydrogen bonds. Finally, we're looking at some observations of trends of hydrides throughout the periodic table. So the first one is that the boiling point of ammonia, which is NH3, is higher than that of phosphine, PH3, which is below it in the periodic table. Now, the reason for this is that ammonia has hydrogen bonding, which we've described on the last question and in lectures, is a very strong interaction, and hydrogen bonding isn't so prevalent and doesn't really have an effect in phosphine. Therefore, the boiling point of ammonia is higher because these extra hydrogen bonding interactions require more energy to break. The second one, we're looking at the melting point of selenium hydride, and that is higher than that of the sulfur hydride. And as in the question before it, selenium is one below sulfur in the periodic table. And the reason that the melting point in this case is higher, hydrogen bonding doesn't really play such a role in H2S. As we looked at in the last question, the electronegativity difference isn't that big, so hydrogen bonding isn't too strong. And what really comes into account here is the London dispersion forces. So if you remember from the videos, London dispersion forces are always present, and they have more of an effect the higher the molecular mass is. And as selenium hydride is lower in the periodic table than the sulfur hydride, there are more London dispersion forces, or like stronger London dispersion forces, in the selenium compound than the sulfur compound. And finally, water, when it's in its liquid phase, is denser than when it's in its solid phase. And this is the opposite for methane. So methane is actually denser as a solid. And in fact, most things usually are denser as a solid. And why is this? Again, this is due to hydrogen bonding. And hydrogen bonding, when you solidify something, has a big effect on the structure of the solid and how it crystallizes. Now, water actually has many different types of ice, believe it or not. There's more than 10 crystal structures of ice known, but the one we're thinking of is normal solid ice when we put water below zero at atmospheric pressure. And this is denser as a liquid because when we solidify it, it has a very open structure. It's going to be hard for me to draw because I'm a rubbish artist. But it forms hydrogen bonds with two neighbouring waters. And this continues throughout the whole solid. And because of this sort of structure directing effect of the hydrogen bonding, it's got a very open structure. And this structure actually collapses when you break it down into a liquid, and the molecules can get closer to each other, and that's why it's more dense. It's got a more open structure as a solid than a liquid. With methane, there is no hydrogen bonding, so there's not this sort of structure directing of the hydrogen bonding. It hasn't got this big open structure as a solid. It's more compact. Therefore, methane as a solid is denser.